Hey pre-calc friends, welcome to Chapter 3. And in Chapter 3 we move on to what things are called exponential and logarithmic functions. So we're going to start with 3.1 today, which is just going to explore a little bit of exponentials. We'll talk about their graphs a little bit, and we'll talk about some really neat real-life applications that we can use exponential functions for. So here is basically what an exponential function looks like. And it's called an exponential function because do you notice where the x is right now? This is an exponential function because look, do you see where the variable is? It is in the exponent, which is why we call it exponential. Okay, so x is there in the exponent, so we're raising that b to the x power, whatever x is. Now the b actually does stand for b for base. Okay, and that's basically what you're multiplying by every single time. So base does have to be a positive number, it's greater than 0, but just not equal to 1. Because if your base was equal to 1, it wouldn't really make a lot of sense. It would just be basically 1 raised to the x power, and it doesn't matter what you plug in for x, you're always going to get 1 out. So we say, okay, the base cannot equal 1, but it just needs to be a positive number. For example, we can have f of x equals 5 to the x. Or we can have f of x equals 10 to the x, or 6 to the x. And all those numbers, the 5 and the 10 and the 6, would be the bases, and the x is the exponent. Okay, well, what happens when we actually graph these, see what they look like? Well, let's give an example, and let's try to just graph one with an xy chart and see what happens. Let's do, how about f of x equals, how about just a simple 2 raised to the x? Okay, xy chart. Let's just plug in some really simple values for x. All right, how about something like 0 and 1 and 2, and then maybe some negatives as well, and just see what happens. All right, so now when we plug in x equals 0 into our function here, you get 2 to the 0. Remember, anything raised to the 0 power is always 1. We get, for x equals 1, you get 2 to the 1. That's just 2. 2 to the 2. Now, 2 to the negative 1, bring back your knowledge of negative exponents, friends. Remember, a negative exponent just means reciprocal, so flip 1 over 2 to the 1. And 2 to the negative 2 would just be 1 over 2 to the 2, or 1 over 4. Okay, so let's take those points, let's actually graph them, x, comma, y. All right, the first one we have is 0, comma, 1, which is about here. We get 1, comma 2, 2, comma 4. Okay, on the left side, how about negative 1, a half? Oh, I'm going to scrunch it in there. And then negative 2, comma 4. That's really tight in there. And as I keep going more to the left, you can see it's going to really snuggle the x-axis. So he's going to come from the left like this, snuggling, and then shoot off exponentially into space. That's kind of neat. So as I walk left to right, if I'm given a b to the x, exponential function, and notice here if my base is greater than 1. On the one I'm doing right now, the base is 2 because it's 2 to the x. It grows, it skyrockets up to left, so we call this one a growth function because as you walk left to right, this one grows. Okay, let's do the same idea over on the right side, but let's pick a different base here. How about f to the x equals, f of x equals 1/2 raised to the x. So now my base here is smaller. It's 1/2. Let's see what happens. XY chart. All right, same numbers. Okay, now it's going to be a little bit tougher because they're fractions, but I know you can do it. Ready? I'm going to get 1/2 to the 0 power, which again, anything to the 0 is just 1. If I plug in 1, that's just 1/2 to the 1, or just 1/2. If I plug in 2, I get 1/2 squared, and that's 1/2 times 1/2, or 1/4. Okay, now 1/2 to a negative power, if you remember your negative powers on fractions, it basically just flips the fraction, and you get 2 over 1, or 2. 1/2 to the negative 1 power is the same thing as 2 over 1, or 2. And similarly, if I plug in negative 2, I get 1/2 to the negative 2. All right, that's going to flip it over and square it. Can you believe that that's actually equal to, oops, 4? There we go. All right, let's plug these values in and see what we get when we graph them. 0, comma 1, 1, comma a half, and 2 comma 4. They're getting really close there. So it looks like if I go really far to the right, it's going to really snuggle there. On the left, watch what happens. How about negative 1 comma 2, and then negative 2 comma 4. So now it's the opposite. As I go to the left, it looks like it's going to skyrocket that way. So how about this graph, friends? All right. So here, this is the type of graph you'll get if you have a typical exponential, b to the x, but now b is a relatively small number, like between 0 and 1. And that works for ours because b was 1 over 2. That's definitely between 0 and 1, right? And look what happens as I walk left to right. Do you see how it gets smaller? It doesn't shoot off to space like we did with the green one. This one gets really smaller, so it decays. So we call this one a decay function. Growth is if my b value is bigger than 1. Decay is if my b is smaller. All right. In the past, we would graph these by hand, and it was actually pretty cool and fun to do, but now we decided to skip that, and all I want you to do is I want you to look at some of these examples here, folks, and I just want to talk about what's the base, and if there's any transformations, can you list them for me? For example, number 1, f of x equals 5 to the x. Now, if the formula is f of x equals b to the x, can you figure out for number 1, what's your base? Did you get 5? Good job. So that's a big one, so that's probably going to be a growth, because 5 is greater than 1. For number 2, there you go, g of x equals b to the x, so b equals 2 over 5. If I graph this would probably be a decay, because that's between 0 and 1. All right, domain and range we don't have to worry about because we're not going to graph. But now, friends, here's what I want you to do. Can you figure out what's the base and what are the transformations? So it's taking us all the way back to section 1.3 when we learned about the whole up, down, left, right, stretch, shrink, and reflections. Let's try number 3. Okay, first of all, there's a lot of stuff on there, but can you figure out what the base is? The trick is the base is always the one that you're raising to a power. And here I'm raising 2 to the power of x minus 1, so my base would be the 2. But now, do you see all this extra stuff over here? What is that? Do you see how that's up next to the x? That's basically raising 2 to the x minus 1 power like that. If my original was 2 to the x, and now I have 2 to the x minus 1, that's a change along the x. And it's addition subtraction, so it's either a left or a right. Ooh, it's x minus 1. Can you figure it out? This is going to the right 1. So it's a 2 to the x graph that's moved to the right 1. Oh, that's pretty cool. How about number 4? Number 4, my base is actually still 2 because it's being raised to the power. So base is 2. But now look at this plus 1. It's on the outside of the function. It's not in with the x, it's on the outside. Kind of takes you back to this kind of function. F of x, but then the plus 1 is out here. Do you remember what kind of transformation that was? Yep, that is up 1. So that's my typical 2 to the x graph. It's a growth, but it's shifting up 1. Domain and range you can skip. One more toughie. Here we go. Let's do it. Can you do number 5? What's the base, and where is it transforming? All right, my base here is 3, because it's being raised to a power of x plus 1. How about the x plus 1? That's in with the x. So that is an x change, and it's plus 1, so he's actually going left 1. Did you get that? Nice job. How about this minus 2 on the outside? Ooh, it is on the outside, right? Because it's on the outside. It's a y change. And it's negative, so it's definitely going down 2. Wow, good job. Domain and range? Nope. One more good example. Ready? Number 6. How about f of x equals... Ready? This one's going to be good. How about negative 4 to the 2x plus 3? Wow, this one's tough. Can you first figure out the base? What's the number that's being raised to a power? Here you go. So base is 4. Now there's lots of things going on. Ooh, were you tempted to say the base was negative 4? That's really, really tempting because negative 4 is being raised to a power, but actually really not. First of all, by order of operations, only the 4 is being raised. And not only that, remember how we learned that base has to be greater than 0? It has to be a positive number. So we can't have a negative 4 as the base, right? But what does that negative do? Do you remember? It's multiplying on the outside. So that is an x-axis reflection. Ah, that's right, that's right. Okay, how about this plus 3? That one's not too bad, right? That's just on the outside, so that's up 3. But it's that 2x that's kind of bothering me. What is that? Okay, that's with the x, and it's multiplying the x, so that's going to be probably some kind of stretch or shrink. But it is multiplying the x, right? So it's going to be a horizontal change, stretch or shrink. It's a 2, which is a big number. Remember with the x's, we always do the opposite. That's a horizontal shrink. So x-axis reflection, up 3, and a horizontal shrink. That's all I want you to do with those. I just want to identify the base and figure out what the transformations are. Okay, that's fine. Now I want to play. And before we play, let's talk a little bit about a new number that you maybe have never heard of. It's called e. E is called the natural number. Why? Because we're going to find that this number occurs a lot in nature. And when we make a function out of it, it's even more popular. It's called the natural exponential function. Okay, now here is how we define it in upper mathematics, but you don't have to worry about this. But look how cool it looks. If we put this in a calculator and it would calculate for us, it would be an irrational number, meaning it goes on forever and ever without really repeating. Basically, you need to think of e as being about 2.72. Would be a really good approximation of what e is. This is the natural number, and again, we use it a lot to represent things that happen in nature, or biology, or statistics, or physics. There's lots of places where the natural number comes in. It's very, very useful. So again, another letter in math that represents a number. Can you think of another one? Yeah, pi. Pi represents a number, 3.14, and so on. So we have e, a natural number that represents 2.72. And when we write it as a function, like you see here, that's called the natural exponential function. Because like I said, e happens a lot in nature. Now, where's one of the best places and most popular that we're going to see? Is banking. Let's talk about some money today. All right, when you put money in the bank, it makes money for you because it's gathering up what we call interest. And the longer you keep money in the bank, the more interest that gets added onto it. But they keep adding, and if your amount that's in the bank is higher, you get a higher interest coming out as well. So it keeps compounding on itself, so we call it compound interest. All right, the equation for compound interest is, it's hard to see, but it is an exponential function because it's being raised to a power, and the power is the t. That's your main variable. That's basically like what x is here. Okay, so first of all, friends, just know that this is a very useful formula that we're going to have to memorize. So I'll put a big star there, maybe make a flashcard or something to help you out. But this one needs to be memorized. Okay, let me label all these letters for you and figure out what they mean. First of all, P of t is the final amount. After you've put money in the bank and time has been spent, how much money do you get out of the bank? That's P of t. T over here just stands for time. How long has the money been in the bank? Generally for banking, we talk about years. So if you know you've put the money in for about 10 years, t is 10. So t here is your main variable, like your x, and that's time. P sub 0, with the little subscript 0 there, just means the p, the principal amount, at starting t equals 0, meaning at the start. What did you first deposit into the bank? So that's your starting or initial amount, and p generally stands for principal, which is just a banking word for the starting amount that you deposited. Okay, so we got P sub 0, we got P of t, R, oh sure, in banking R is your interest rate, but this is interesting because generally when we talk about interest rate, we talk about percentage. This account has a 5.25% interest rate. Great, great, that's great, I love it. But you have to, in math, in pre-calc, you have to change all your decimals into, all your percentages into decimals. Do you remember how to do that? For example, if I give you 5.25% interest rate, how do we change that to a decimal? Do you remember? We change it by moving it 2 spots to the left of the decimal place. So 5.25% is really 0.0525. All right, so as we use interest rates and we use R, we must always change it to a decimal first, by moving it 2 places to the left. All right, that leaves one last letter. It's this N here, and the N here is the same. This tells you how often is the bank compounding your interest. And sometimes banks advertise it in different ways. Some banks will say, we will compound you annually on your account. If you see the word annually, that N just means 1. N stands for the number of times the bank is compounding your money per year. So if they say annually, N is 1 because you're compounding once per year. That's what annually means. If you're compounding monthly, monthly is how many times per year? 12. So if you see monthly in a problem, you know your N value is 12. And similarly, if you see quarterly, quarterly means 4 times, like 4 quarters in a dollar. If it's quarterly, then it happens 4 times per year. If we said something like daily, if it was compounding daily, that would be a lot. What would your N value be? Well, in 1 year, if you're compounding daily, that's how many times? 365. Exactly. There you go. So memorize that formula, friends, and that's what all the letters are there for. Now we get to play. Ready? Now you definitely need your calculator with you if you don't have it yet. Great example. Number 1. Suppose you have $100 and you're at a 5.5% interest rate. How much money will you get after 2 years if the bank is compounding everything? For number 1 is annually, for number 2 will be quarterly, and number 3 will be monthly. And by changing the words, all you're basically changing is the N values. That's it. All right, so let's pick out our formula here. This is P of T equals. Now, before I just jump in, let's label some of the things that I marked up here in the problem. What's the $100? If that's what you actually deposit, that's what you started with, that is P subscript 0. That's your starting amount. How about 5.5%? What is that? Oh, it's rate, right? So that's your R, but we have to change it to a decimal. So 5.5 should be 0. Move it 2 places to the left, 0.55. You can check if that's right by just moving the decimal place 2 parts to the right and see if you get the original interest rate percentage. Okay, how much? We're asking for P of T. What's the final amount? After 2 years. And 2 years is T. I think we're good to go. Shall we plug it in? Here we go, friends. This should be P sub 0, which is $100, using our brand new formula, times 1 plus the rate over N. The rate here is 0.055 over N. What's N in number 1? Annually, it says, right? This is annually. Remember, if it's annually, that's how many times per year? It's once. So I'm going to put N equals 1 here in the denominator. And then we're going to raise it to the N times T. Well, N is the same N, that's 1. And T is how much time was in there? 2 years. Great. Now, we got to put this in the calculator. Okay, watch this, friends. Ready? There's a really good order to do all these that's not too confusing. Here's what I would do. I would first do this fraction right here. Here's step 1. Do the R over N first. This one's really easy because you're just dividing by 1, but sometimes it's really complicated. So put that in the calculator first, hit Enter. Good. Number 2, go ahead and add 1 to your answer. And if you remember, on your calculator, all the way in the bottom, right above the negative sign, you have that special ants button. That is just going to bring up the answer you got on the previous answer. Use that. That's a really helpful button, so you don't have to keep retyping your answer. Just use ants, and it'll remember what you just did. Okay, you did that. You added 1 to your ants. Hit Enter. Now, third thing is you're going to raise it using the raising the exponent button. And that is basically, you can raise it to whatever power you want using the little caret symbol, which is right above the division symbol on your calculator. Raise it to the, here I'm going to raise it to the 2. Enter. And then last step is I'm going to plow forward and multiply with the 100 in the front. Okay, so I'm going to actually talk through this as I'm on my calculator. First step, I'm going to do 0.055 divided by 1, and I hit Enter. I get 0.055. I'm going to immediately hit plus, and when I hit the plus sign, if you notice on your calculator, it brings up ants. That's awesome, so you don't have to type ants or use the ants button. So I'm going to type plus, and it said answer plus 1, hit Enter, and I get 1.055. Now I'm going to use the raising button, and again, when I push the raising button, it says answer raised to the, well, my N times T is 2 times 1 or 2, so I raised to the 2. That gives me 1.113025. And last step is I'm going to multiply by 100. All right. So for number 1, my final answer, friends, is $111 and now 2 decimal places, right, for dollars and cents. It's 3025. I'm just going to round it to 30. All right, that's my final answer for number 1. So you started with $100. You have a pretty good interest rate. It was in there for 2 years, and you made what? $11.30. That's not bad. That's easy money. All right, ready? Let's try number 2. Let's try quarterly. And the good thing is everything is going to be about the same, except if you look on your equation here, this is going to change here. The 1 is going to change to what? Quarterly is 4 for n, right? And then up here in the exponent, instead of 1, it's going to be a 4. Let me write that out. I'm going to say P of t equals starting amount 1 plus my rate, 0.055, divided by quarterly now, so that's 4. And raised to the, not 1, it's 4 now times, what was the time? 2 years. Okay, ready? I'm going to do this one first. Hit enter. Add 1. Raise it to the 8th power, because it's 4 times 2. And then multiply by the 100 in front. Okay, ready? I'll talk you through it. Here's 0.055 divided by 4. Enter. I get about 0.01375. That looks okay. I'm going to immediately hit the plus sign, plus, and it takes my answer button. Plus 1. And I'm going to use the raising symbol, raised to the 4 times 2 is 8, so I'm just going to type in 8. And I get a long number, 1.115441858. Does that match yours? And then we're going to say multiply by $100, your starting amount. And here we go. I get $111 and 54418 whatever. Let's just round to 54. 2 decimal places for dollars and cents. All right, so that made a little bit more by compounding a little bit more. Now, we're not making a ton of money. Why not? Well, we're not depositing a lot of money. It's only $100. If you try putting in $10,000, $100,000 or $1 million, it's going to be a lot more that's going to be added on. Your interest rate is pretty good. You can have a little bit higher. And always, if you just keep money in the bank for a longer period of time, it tends to make a lot more money. So we're not doing a bad job for what we've done, but a higher interest rate, more deposit, and longer time will always help. All right, do you want to try number 3 on your own, friends? This is monthly, so now what's your n value? 12. All right, here's my equation. Over 12 raised to the 12 times time, which is 2. Okay, I'm not going to mark the steps. I'm going to see if you guys can do it now. I'm going to put it in my calculator and doing all the steps, and we'll see if it works out okay. And I get final answer. How about this, friends? I get $111, and I'm going to round this one because I get $599. So I'm going to round it to 60 for 60 cents. And there you go, friends. So we're using exponential functions because the t value, the time, is your main variable, and it's in the exponent. It's right here as a power. So exponential functions are really useful for things like this, for banking. Okay, that's great, but what if? What if we do faster than monthly? What if we do daily? That's 365, right? What if we do every second? Oh my gosh, if it compounded every second, that'd be so huge and you'd be making much more money. What's faster than every second? I don't know. But what banks do sometimes is they compound what's called continuously. It is continuously compounding the interest onto your account, so you're continuously getting more money. And to do continuously, we need something faster that maps and marks what this is. Well, we have a brand new number, right? We have E. E will be able to show this new type of continuous compounding. And look at this. Here's your new formula. I show above it the steps that it takes to get there, but that's a little bit boring. I'm saying don't worry about it. Here is your new formula. So 2 formulas today. The first one you learned is just for regular compound interest. But this one, star next to it, memorize please, is only if you see the word continuously. If you ever see that we're compounding continuously, we use this formula. Some people call it the PERT formula because it looks like P-E-R-T. PERT. If you've heard of PERT, that green bottle shampoo, this is the PERT formula. It's still, the starting amount, and now you just use the E button on your calculator, raised to the rate times time. Okay, now these are pretty easy because you can put this in one step. Ready? Let's try. Last example of the day. Let's suppose you invest $200 at 7.25 interest rate. How much would you have after 10 years if the interest is compounded? Oh, there it is, continuously. So right now I'm thinking PERT. Right away, using our brand new formula. All right, let's listen to what we got here. I'm going to invest $200. I'm going to start with that. That's your starting amount. 7.25, that's your rate, but really decimal, right? How about 0.0725 as a decimal place? Okay, and then 10 years is your T time. All right, let's find P of T and see what we get. All right, new formula right here, friends. P of T equals starting amount times E, the new natural number, raised to the rate times time. All right, your starting amount was $200 times E raised to the, your rate is 0.0725 times your time. You're in there for 10 years. All right, luckily, friends, this is really easy, like I said, to do in one statement. So I would literally punch into the calculator 200, and can you find the E button? Specifically, can you find the E raised to the button? There's an E button that's right above the division symbol, but there's a better one that's right above the LN. Do you see the LN button? It's all the way on the left-hand side near the bottom, kind of third from the top. You see LN, or it kind of looks like IN, but it's LN. You see E raised to the X, hit that, and you get E raised to the, it'll open up a parenthesis or put it up in the exponent, and you can write 0.0725 times, you can use the times button, 10. And do that in one statement, and then you can hit enter. Ready? I'm going to do it. 200, second ln button, e to the 0.0725 times 10, and hit enter. All right, friends, you want to see how we did? I got about $412, and 946 rounds up to 95 cents. So pretty good. It was in there for 10 years. That's a long time. A little bit more money, a much higher interest rate, and you're compounding continuously, which is going to be a little bit more. All right, there you go, friends. So there's a really good example in real life of how we use exponential functions. They're perfect for banking. So you've got our brand new formula. You've got two of them, right? Here's our original one. This is just regular compound interest. And then this is if you're compounding continuously. I guess the hardest thing really is just using the calculator, knowing how to plug it in, and feeling comfy with that. All right, friends, there's the beginning of Chapter 3, 3.1. Hopefully it went okay, and I'll see you next time. Great job, everybody.